Okay, class, we're going to cover the operator. We're going to learn something called the del operator. And we're going to talk about how to use that del operator to do something we've already done, which is gradients, curl. That'll be this video, and next video, divergence. And so these are operations, in this case, on a scalar field. So that was our function. Z is a function of x and y, maybe it's x squared plus y squared. We learned how to actually apply this new operator and get a gradient. But now we're going to apply this new operator to, rather than a scalar function, a vector function. That's this chapter, vector functions. And so we're going to do an example. We're going to work through it computationally, and then we'll come back and try to understand visually and geometrically what curl is actually doing. We're going to take a look at this sink draining vector field we've done a few times already in this chapter. And so it's an approximation of what actually happens, the swirling that happens in a sink draining. So this is an R3 vector field, and we have our three components. And what we ultimately want to do is figure out how to use this new operator to get the curl, and then what is that curl going to computationally give us. And lastly, we're going to go ahead and compute the curl vector at different points through the field. Okay, so let's maybe start off, let's visualize this for a moment, and then we'll come back for our del operator. So we've done this several times already at this point using CalcPlot 3D to visualize the vector field. So I entered the vector field, the M, N, and P components. Because we are in R3, I decided to use a constant primary color, and there's that swirling motion that we've talked about. Okay, now how are we going to get the curl? And again, what is that going to mean? We're going to get there. Let's start with this example now. So the del operator, in R3, a del operator has three components. If you had just an R2, so maybe let's do a little review over here. I think there's some space. So if we had Z is a function of x and y, and let's say that that is, we'll just do our easy circular paraboloid. This is an R3 surface. And then if we were going to do the del operator, well, there's only two inputs. So the del operator would just have two components for the two independent variables. So that's a two-dimensional thing. And really what we're doing when we've done a gradient of f of x, y, really what we can think about this is doing is scalar multiplication of this vector on this scalar. And so we get a two-dimensional vector when we're done. We started with a two-dimensional vector with the partial with respect to x. So we were actually applying a partial differentiation of del x. So I'll write it out long ways here. Applying del x to our function, oops, and then applying del y, the partial with respect to y, to the scalar function. And we just did this, again, we didn't do it so many steps here. We just said, okay, what's the partial of that with respect to x? That's the first component in the gradient, partial with respect to y, second component in the gradient. And we did lots of stuff with that gradient then. But this was just to show you that this del is actually operating on the scalar function. So just to remind you, this is something we already know how to do in another way, but we want to just sort of take a little rotated view, get another way of thinking about computing gradients through this new thing, this del operator. The reason I'm kind of stressing that is because I think that's going to help us when we do these things like curl and divergence. So we have a del operator, and we can think of this as scalar multiplication. To compute curl, we can think of that as a del operator, as a vector on a vector. And so we can do a cross product. Or we can take two vectors, the del operator vector and the vector field, and dot them. So these are common ways of combining things. What's new is this operator. Okay, so the operator, again, isn't a function, it isn't scalars and numbers and a vector. It's a vector that operates on things. So now let's come over here to our example, make some space. Let's just start seeing what happens when we apply our definitions here for curl. curl, and then we'll see what it means. So let's just crank away the computation first. So we have a 3-dimensional vector. So we're going to need the 3-dimensional del operator, which is here. Again, we just looked at the first one. It was an R2 del operator. Now we're going to look at an R3 del operator. And we're going to do a cross product of that with this field. So curl of a vector field. And we do the matrix method, I, J, K, which is really just getting a determinant if you're in linear algebra. And we're first going to do the del operator in the first row, or second row, I guess, del y. Then the final row contains the vector field component by component. Okay, and because we have two input vectors that are in R3 and we cross them, we know a vector and a vector crossed make another vector a third vector. So we're trying to get curl, which is going to be another R3 vector. Okay, remove the first row and column, and then you look at the diagonal minus what happens on the anti-diagonal. So del y of this thing has no y's in it, so 0 minus what happens in this component. So that's really, maybe I'll write it like this because we're going to do it with respect to z, minus x z to the minus 1. So we're going to subtract when we do this multiplication, which is really an operator on this. So we need to take the derivative of negative x z to the negative 1 with respect to z times the power down the power. So in the first component, we'll have a negative negative, so make an x z to the negative 2, so z squared. Right? Now our second component, we remove the second row and column. We do our diagonals minus what happens in the anti-diagonal and negate that. And don't forget the next one's going to have a negative. Okay, so we said this times this. When x looks at this, it's all constant, so that's a 0. And then derivative with respect to z of y, z, so maybe we'll do the same thing. We'll write this as y, z to the minus 1. And now when we do the partial, we'll have times the power down the power, so negative y over z squared, and then hit it with another negative, makes it a positive y over z squared. Okay, and then one more component we need to get. The final one, remove the row and column containing k. So what we're left with is this and this. So these are partials now. We can do both of those. That involves an x and an x. So maybe we'll write this back. What it was. And this one was y over z. Okay, with respect to x, is negative 1 over z. Yes, negative 1 over z. Minus negative 1 over z. Okay, so there's the computation of our curl. Okay, so we can combine some terms at the end. That's minus 2 over z. And I feel like I got to sign off on this. So let me check the first component. Remove that and that. So this time it's a 0 minus. That'll be minus, becomes a plus. Oh, but then the minus for the minus diagonal. There's our minus x over z squared. And then the second one, remove that. So that times out 0 minus y times z to the minus 1. And that's a minus, a minus. Oh, and then another minus because that's the second component. So there we go. All right. checking the arithmetic on that. Okay, so this, what does this mean at this point? We just did a calculation, which was really a review of something from several chapters earlier, a cross product of the one vector, which is really just an operator, with another vector, which wasn't a scalar. So normally when we've done these, we had a scalar and scalar. Now we have an operator and a function. Each component has variables in it. And so what we are left with is now also itself. We started with an R3 vector field, and we end with an R3 vector field. And so the vector field that we had looked at, let's go back to that guy. Oops. Okay, background. Okay, so we were with CalcPlot3D, show the vector field. This is the vector field itself. And let me pause while I enter the next one. Okay, so what we've got here now is we've got two of them, so let's take them out. Here's our curl vector field. And let's see if we can put a constant primary color, let's make that guy red. It looks like everybody's pointing. It's using the arrow keyboard, kind of getting different views. Pointing towards downwards towards the origin and then upwards maybe towards the origin. And that is the curl vector field associated with this sink draining field. Now, the problem said compute a couple things, compute some vectors. So let's go back and maybe, let's see if I have, we get some room over here. The curl at the point 1, 1, 1. So curl of the vector field at the point 1, 1, 1. Just says plug in 1 for x, 1 for y, 1 for z. So -1 over 1 squared is -1. -1 over 1 squared, -1. -2 over 1, -2. All right, so that is a vector at a point. We know how to enter those into CalcPlot3D. And we want to compare that with the curl at another point. -1, -2, 1. So when x is -1, so I'll have 1 over 1 is 1. Negative of a -2 is +2 over 1 is 2. And -2 over 1 is -2. Okay, so two vectors at particular points in the field. I go to a point in the field and I have a vector that's pointing in some direction. Another point, similar, -1, -2, 1, I have another vector. What do those mean? So let's check that out. So we know how to plot those in CalcPlot3D, but there's also some tools as well in CalcPlot3D that make that even easier than entering, right? We could select a point, select a vector, add those points shifted from their vector. Curl vectors shifted up to those points. But there's also some tools in the vector field. So down here, Paul Seeberger, the creator of this, has been adding some more stuff. So he's got some options where we've already looked at earlier in the chapter, flow lines. So you can select a point. View there, and we can select a point. Oh, shucks. Keep grabbing the wrong thing, sorry. All right, so here's the point. I'm going to grab it in here. And then we can show, and you can enter the components of the point. Say we wanted to look at the 1, 1, 1, 1, rather than dragging the slider bar. Okay, so there's our point. And then what it is automatically displayed is the flow line solution. So this is where we see a point that starts here in the sink draining vector field, follows those vectors, it does the vector hopping, and starts swirling and swirling. And really, again, it's approximation. The drain would kind of get closer, funnel-like, closer towards the drain. But we're circling around and we end up there. Or you can show the curl at a point. Okay, so this is a really cool visualization because what's happening here, the yellow vector is what we just computed. At the point 1, 1, 1, the curl vector is this three-dimensional vector, -1, -1, -2. And that makes sense. It's pointing down and sort of back. Right, here's our positive x, positive y. So we're going down in the z, down, back behind there in the x and y. So we have this point in space in this vector. This little pinwheel is showing what happened. So we saw that starting at the point 1, 1, 1, we would follow the direction given by the flow line. So that's sort of what's called a macroscopic type of circulation in the field. So if you inject a point or a dust particle into this field, it's an airflow field, or this one's a water flow, it's going to move like the flow line in a large sense, a macroscopic type of motion here, which is circulatory for this particular vector field. And yet, there's another type of motion that's happening, and that's what curl is measuring. Curl gives us the microscopic circulation of a point. In this case, a point piece of particle that's in the fluid, or if we're in an airflow vector field, a dust particle. It's not only moving through the air like that, it's also spinning as it does that. And it's spinning, how it spins, is according to the axis given by the curl vector. So that's the yellow one, gold one here. So it's spinning in a way perpendicular to that. So this is like a normal vector of circulation, microscopic circulation. And then when it moves along the flow line to another point, there's a different curl vector, it might change a bit. So it's going to spin around a different axis. So this is what is called an axis of revolution. That curl vector here, -1, -1, -2, the gold one on the screen, represents the axis of revolution of that microscopic circulation. And then the next thing, if you were to get the length of each of these vectors, we know how to do that, the magnitude of the vector, right? The sum of the square root of squared. So we sum them up, 1, 1, 4, 6, that's square root of 6. So that's the length of that vector. Turns out that's a little bit different than the length of this vector. This one is 4, 4, 1, 9, square root of 3. So this one is a little bit longer, its length, at this second point. And what that length has to do, so again, the vector itself gives you, and let's maybe move this so you can see, the vector itself gives you the axis of rotation of microscopic circulation, and then the length of that vector gives you the rate of rotation. So the longer ones are going to spin faster than the shorter ones. So let's see what happens if we can move to, what was our other point? -1, -2, 1. -1, -2, 1. Okay, so now we're over here. A different curl vector, that's the one we computed here, the vector 1, 2, -2, also kind of pointing down, but away, and a positive x, positive y. So that vector gives us our axis of rotation, and notice that pinwheel is always perpendicular to that, and then the rate at which it is changing. And so you can play around with this and pick maybe a lot of different points in the field to see, and you can visually see from its length how quickly it's going to spin. Okay, so summarizing a few things about curl. Curl, first thing, definition. It is a if you have a three-dimensional vector field, R3 vector field, you need an R3 del operator. You're going to cross that through a cross product, which means you can use the determinant to compute that. You will get a vector field itself out. So if you have an R3 vector field, curls an R3 vector field itself. And that tells you at any point in your field, it tells you microscopic circulation, microscopic rotation. So you go to a point in the field, not only is that particle moving through the field in the same direction, it is moving and spinning as it does that. And it spins, spinning this way, spinning that way, depending on how the axis of rotation given by the curl vector moves through there. And then the rate of it is given, the rate of that rotation is given by the length of the vector. So that's a really cool observation and something super useful about R3 vector fields. You have a couple activities that I think will really help solidify this for you. Towards the end about curl, where you can take, go to a sink, actually do this, put some little pieces of paper, watch what happens, shoot a video, with a toilet, flushing the toilet. You can do it in your, just a glass of water or coffee or something, and watch how things spin and rotate. The two different types of rotation, again, those key things. Flow lines are macro, and then curls are micro rotations. All right, so the next thing we're going to do the next video, which is a del operator on a vector field, but a different one. We're going to do a dot of those. We'll see what we get by doing that. Okay, just wanted to share, I found a couple points in the CalcPlot 3D tool that I think will help visualize the rate of rotation. Okay, so here's a point. I just played around and found some points. Here's a point, -4 for the x, -1 for the y, z1. We compute the, follow the formula, get our curl vector field, plug in the point, -4, -1, 1, and here's our curl vector. It's pointing us in the direction that gives us an axis of rotation. And here's our pinwheel. But let's see what happens if we change just one of these components. Okay, so here's another vector, still spinning, perpendicular to that rotation, but let's maybe try if we can get it going a little faster. Okay, so this vector now, much longer, hard to see from this angle, but there. Okay, so that vector is longer than the other two that we've already gotten. And you can see it's spinning quite a bit faster because the length of that vector gives the rate of rotation. Find some points, play around, and you can make these visualizations concrete for you.